So back in early 2000, in order to face a dramatic increase of volume of data out there, industry and academia got very interested in peer-to-peer systems for the fantastic potential for scalability. More specifically, these systems were very popular to implement file-sharing applications. And such systems, most of the time, were relying on what we call distributed hash table. So the goal of a distributed hash table is to distribute the responsibility of storing data on a very large set of nodes and access them very efficiently. Now, when it comes to a peer-to-peer system, the objective of such a system is actually that there is no longer a server somewhere in the system, and machines can act both as clients and servers. What that means is that this is very scalable in the sense that when the number of clients increases, then the number of servers increases linearly. So this peer-to-peer system has been used in many systems such as, for example, Skype or Emule or BitTorrent. And we are going to see today how they work in practice. So a peer-to-peer system builds what we call an overlay network on top of the IP infrastructure. And what a DHT does is that starting from a data, say a movie, the system attributes a key to that movie by using a hash function in order to do some specific operations such as inserting pairs key value, in that case a key and the movie, but also looking for that information in a large system just by having the key. Now consider the example where starting from this node as a source, we want to have a lookup at this specific movie that we know what is the key. And that movie is stored at a given node that we can index by the key, so that one, and you can then retrieve the movie from that node. So the goal of the peer-to-peer system is actually to implement the routing to go from one source to a destination. This in turn would mean having the routing algorithm to go from any source to a key destination in the network. There are several peer-to-peer systems, but in the context of this video, we're going to consider Pastry. So in Pastry, each node is assigned a given node ID of length 128 bits that place it in the following range. Each key gets assigned an ID in a larger space than the node ID, which also places it in a given range. So what that means is that node and key cohabit on a circular ring, and the first question is to assign responsibility to node. So basically, who is going to be responsible for a given key? So in Pastry, the responsibility of a given key is assigned to the node which is numerically closest to the key ID. So in that case, node 1 here would be responsible for this key. So what that means is that whenever we do a given operation, so a routing operation or a lookup operation or an insert operation to a given key, what the system does is that it sends a message to node 1. So for example, this key 2 here is going to be hosted by this node 2 here, such that whenever we send an operation, we do an operation on key 2, then it's going to send a message to node 2. If for one reason this node 2 is no longer there or has been faulty, then the system will automatically reassign the key. So the key is automatically going to be assigned to node 3 here, so that whenever now there is an operation done on key 2, then the message is automatically going to send it to node 3. The goal of the Pastry algorithm is to be able to route a message from any source towards any key destination in the network. At one end of the spectrum, the two things we need to consider is the number of routing hops to reach the destination, and also what is information that each node needs to maintain so that the routing is possible. So at one end of the spectrum, you can imagine that each node has the global index. In that case, the routing is going to be done in one hop because everyone has a global index of where is every key. But the downside of this is that every node needs to maintain the entire information, and this is prohibitively expensive when it comes to very large systems. At the other end of the spectrum, you can store minimum amount of information, say the successor and the predecessor, and then you can route by going from one node to the other until you reach the destination. In that case, what you actually minimize is the number of information that you need to store, in that case just a link to the two neighbors, but then the routing operation is going to happen in about log n hops. So now let's see how the routing algorithm of Pastry works. So say you are starting from a source node and you want to route to a specific key, which is D4, 6A, 1C and some other thing. which is here and hosted by the node D4CA1E. The Pastry routing algorithms works with prefix-based matching, and what it does at each hop, it's going to get closer and closer to the destination. So this is what we call a greedy algorithm. So the first routing step is going to fix the first digit, which is a set of 4 bits, so that we get closer to the destination. With this, what this node is going to do is that it's going to send to any node which actually starts with a D that he knows about. So say this is this node. So the message is going to be forwarded to that node. At the second step of the routing, then this message is going to be sent to a node which ID matches even more the destination, say by 2 digits, which is going to be sent to the node D4213F and something. And so on and so forth. At the next hop, the prefix of the node is going to match even further the destination by D46 and something until it reaches the destination. So what we see here is that we have a reasonable number of steps for routing. We'll get back to this later. Now let's see what is the information that each node needs to maintain for such an algorithm to be implemented. So let's have a look at the routing information which is stored in the routing table that this node 65A1FC, for example, has to maintain. So the way the algorithm works is that it's basically going to reduce this destination space each time. And the first hop, what it needs to do is that sends this message to any node that matches the destination with 1 digit. So that means that it needs a representative of a node starting with a D. That way it's going to reduce the search space to 1/16 of the namespace. At the second hop, it's going to again reduce even further that space by dividing the namespace that it has to consider, and so on and so forth. So what that means is that at the first level of the routing table, this node here needs to be able to match the first digit of any key. So that means that it needs to have a node, knows about a node starting with a 0, and obviously its IP address to forward the message to. So that any key starting with a 0, it can take care of and route this message to that node. But it needs also to know about the node which ID starts with a 1 and its IP address, but also with a 2 and so on and so forth. So note that for its own, that the entry that would start with a 6, it acts here at its own representative for that space. At the second level of the routing table, that means that it would be to participate to a routing and use this second row of the routing table. It would be that node would be the second step. So that means that it would have been contacted because it was matching already the destination key with the 6. In order to move forward to any key starting with a 6, you need to know a node starting with a 6 and a 0 and its IP address, and then a node starting with a 6 and a 1 and its IP address, and so on and so forth. Again, when it comes to 6 and 5, it acts as its own representative. Next level of the routing table, well, it will have representative matching more and more its own ID. So that would be 6, 5 and then 0 and something, and then its IP address, 6, 5, 1 and something, and then its IP address, and so on and so forth. With such an algorithm, what we see is that we can provide a routing algorithm that fix a routing in a logarithmic number of hops in the size of the systems, but also that the state that each one has to maintain is a logarithmic number of line of the routing table. So this was the example of the Pastry routing algorithm, but there are other peer-to-peer systems that work with similar algorithms, such as, for example, Cord and Core Academia. You can find in related videos how to insert a node, how to delete a node from such a system, but also how to account for geographical locality.